Good morning, everybody. I hope everybody is doing fine. We will continue our discussion on the introduction to operating systems. This is the third week of the semester. As you see, the introduction is taking quite a lot of time. That is expected because, as I mentioned at the beginning of the semester, um, before going into the details of all the concepts of operating systems, we like to go over the main concepts, because when I start talking about processes, which is the next chapter, it will be important to know about the memory or the input output devices or the system calls, etc. Okay, so before to go into the details of everything, we need to know some we need to know some stuff about each of the operating system concepts, at least to some extent. So last week, I think we stopped somewhere around here. We said that to be able to communicate with the operating systems as programmers, we need the API. Okay, we need the functions to call. Usually, when you try to connect with the operating system, talk to the operating system, we prefer the C programming language, and the POSIX, the standard for the Unix operating system, defines about 100 procedure calls. The book very intentionally makes a distinction between procedure calls and system calls. System call is a system call, that's a regular thing. It is a system call that we defined here in this picture. When you say read something from the desk, some open file, this is what happens. We will trap to the operating system, and operating system handles it, and some other process or our process would get back the CPU. That's what we say. But the POSIX doesn't say that you need to have these operating system call or system call. It says that there are 100 procedure calls. So it is up to the implementer of the operating system to handle these procedure calls in the user space or the kernel space. Okay, maybe some of the calls are so simple they don't have to go to the operating system. For example, print system calls. Okay, when you like to print something to the screen, for example, you need the operating system. But if you print everything one by one, characters one by one, and every time you make a system call, that's going to be too expensive, because operating system calls are too expensive. We are going to talk about it. Okay, you don't want to do too many operating system calls, because every time you do the operating system call, you need to change the run mode from user mode to kernel mode, and etc. You need to save lots of data to come back, and you need to do, the operating system has to do many tasks, like the housekeeping task and etc. So you like to keep your operating system calls to a lower level. Don't make too frequent operating system calls. So sometimes we like to handle this kind of simple stuff in our user space. For example, instead of printing the strings character by character one by one, we will keep them in a buffer. When the buffer is full, then we would make a system call. Okay, then we would make a system call, and this comes sometimes surprising for some people, but this is what happens. So again, procedure calls and system calls are different, and POSIX defines procedure calls. Okay, let's look at some of these calls regarding the process management. One of them is fork. Fork is the only way to make a new process in Unix. Unix like operating systems such as Linux. Okay, so fork is to create a process. So how does it behave? It says that I am going to make a process which is the exact copy of the parent process. Okay, it will be a copy, it will be a new process, but it will be exact copy. Okay, another one is execution. Okay, it doesn't make much sense to keep two copies of the same process. They are doing exactly the same. So usually the child process changes its core image. It says that, okay, I don't want to be my parent anymore. I am going to change my image on the memory with this program on the desk. So you give the program name on the desk, and these are my arguments, and these are my environment variables. Okay, what are the environment variables? We know the parameters. The environment variables are the variables that the system uses. For example, on my sudo shell program, my environment variables are these. There are many stuff in it. Some of them are really scripts actually. I don't. Should I wait? Okay, many of them are scripts. I will cut it. I cannot cut it now. Can I do this? No, because it already dumped everything. Okay, I know what to do. Just kill it. And if I like to echo, for example, path. For example, path. Yeah, this is my path environment variable. You know what path is, right? Path is the list of directories. Okay, when I say ls, okay, the shell script first looks at your shell script first looks at the path environment variable. It says that where is ls? Ls could be in this directory, user local s bin. If it is not there, then it could be in user local bin. If it is not there, it is user s bin, etc. So it is scanned. So there are many other types of environment variables. Path is one of them. Okay, so these are all passed to this exec ve procedure call. And then we have wait PID. We wait until the child terminates. There are options for this one. Okay, and there is exit procedure call. We say that okay, I am done. I am asking operating system to kill my process. Okay, that's one way to kill a process. Okay, and I guess we looked at this code and we discussed about the exit, right? Exit command, because exit command should not be executed. If the exit command is executed with the exec VE, then it terminates itself, nothing else. Good, so I think last time we did this and we stopped. Are there any questions up to now?
Sir, in the last lecture, you asked about what is the problem if we call him exec and you said try to think about it. I tried to think about it, but I couldn't really figure out what is the problem, how could be it's prevented if we do not using exit in exec. Could you explain or
Oh, okay, so last time I think some people answered it actually, and I thought that it is kind of clear. If it is not clear, then you look it up. Okay, let me talk about it a little bit more then. Suppose this is my shell, okay? When I say ls, where is ls? Okay, what was the command for? Where is ls? Yeah, ls is here, okay? Bin ls. Under the directory bin, okay, there is a ls command, okay? And when I say what other program do we know? We know grep, right? Where is grep? Grep is again at bin grep. So I know where that is. But where is exit? Okay. I don't see the exit command anywhere. Okay. These are the manual pages for exit. They are not exit command. So there is no exit command. But when I type exit, it runs and it kills my shell. So how is this happening? That was the question. The answer is exit is handled specifically in this infinite loop. Okay, there is a there is a there is a there is a exception if statement. It says that if strcmp command and exit, if the command is same as exit, right, then what should I do? Then I should maybe call, let me make this a little bit smaller. Okay, then I should maybe just call the exit procedure. Okay, so I am handling it specifically. I am not forking, and I am not executing another program, because I am trying to kill this process. I am not trying to kill a child process that kills itself. This one is creating a child process that runs ls. Okay, I cannot do the same thing with the exit command, because if I do that, I would create a child process that would execute exit. That doesn't make any sense, because that program is going to terminate anywhere. But the here, what I am trying to do is I am trying to kill this shell process. Okay, does that make sense, Bilal?
Yes, sir. Thank you for clear
Okay, any other,
explanation.
okay, any other questions about exit? Of course this is of course this is only a very simple, very simple shell. Okay, very simple shell. There are many other stuff that this doesn't do. For example, I could have run this, right? ls minus what would I, okay, alt, and let me pipe it. Okay, so I'm using piping, right? And wc minus l. So it is going to run two processes. Okay, I am going to run fork two times, one for this one and one for this one, and I need to connect the output of this one to the input of this one, right? Who's going to do this? Shell is going to do that, right? Shell is going to do that. Okay, so shell is more complicated than that. Or maybe I could do this, lsalrt, and where is my ampersand sign? Okay, I found it. So what does this mean? Run this in the background, right? This means that run this in the background. So it is running in the background. While it is running, I can do some other stuff. While it is running, I can run exit. See, when I run exit, it exited from my shell, and the ls is killed too. So these are all handled by the shell program, and the shell program is not that easy to write. And in fact, uh, document for bash, if you look at the bash document, it is complicated. I mean, it is not easy to it is not easy to remember all the details of a shell as complicated as bash or C shell or the TC shell. See, this is the contents of this document, right? Okay, so how many pages is this? Okay, hundreds of pages. What are these? Oh, okay, so these are the number of sections, maybe. Yeah, POSIX mod, POSIX correctly variables is set. So these are some of the variables that we defined here. And in fact, these bash scripts, okay, these scripts, they define their own languages, right? You could say things like, I don't remember now, but for each $a in ls, does it work that way? Echo, no. What does it say? For each, not font. For a, yeah, okay. in ls echo $a. Didn't like it, so I forgot how to write this one. So you could write for loops, you could write if statements, you could write many switch kind of stuff, and you can write your own scripts. And in fact, when I show you the environment variables, I think many of the environment variables were scripts for bash. Bash script for loop. Okay, many people ask this question, and okay, so you look at it. Okay, for variable in something do. Okay, I forgot do and done. Okay. Okay, for output in something Linux command, then do this. Okay, anyway, um, let's go back to the slides. Again, this is a very simple bash, a very simple shell. Just an example. It ignores many things. Okay, what kind of other procedure calls we have defined by POSIX? File management is very important, and most of them you already know. Okay, you already know about the library calls. Open library call, it opens a file, closes a file, read, write, seek, and the status of information. Okay, status information, you already know about them because these are parts of the standard C libraries, right? Standard C libraries, and many of them inside, as you know, calls makes a system call. They don't have to, but many of them makes a system call. Especially this write. Okay, write doesn't make an immediate system call. It tries to kill. It tries to fill a buffer first. When the buffer is filled, then okay, you make a system call. I mean, the library makes a system call. Okay, go. So these are the file management calls, and these are the, again, other types of file management about the directories: make directory, remove directory, link, unlink, mount, and unmount. Okay, we linking and unlinking, I think I am going to show an example. Mounting and unmounting, I am going to show another example too. So if you don't know about these, read about them. These are important. Well, anyway, I mean, the systems programming course that you are taking this semester is about using this API, this POSIX API. Okay, you are going to use these system calls to write programs. Okay, and you are writing the program for the systems programming. It is not for and user stuff. I mean, it is not. What is PowerPoint? PowerPoint is an application, user application. We use PowerPoint to make presentations. Okay, we use the PowerPoint for our own purpose, and that's an end product. But what is a compiler? Compiler is not an end product. Okay, we don't make money with the compiler. Okay, we use compiler as a tool to produce our application programs which make money for us. Okay, so systems programming produces these kind of programs, and these kind of programs, system programs, are usually produced using the operating system calls. Okay, so Erhan is going to teach you many of these. What else? Change directory, change mode, kill, and time. Change directory is another. Change directory is another command that is not executed using the execve, because when you change the directory, you are changing your environment variable. Remember the execve takes the environment variable. It is the environment variable of the child process. So I don't think that where is okay, I cannot find it. It's same as exit. Okay, So it has to be executed, it has to be handled as an exception in my infinite loop of the shell. Because this one says that I am changing my current directory of this shell, but this, if it's a child process, it changes its own environment variable, not the parent process's environment variable. Okay, so that's another one. This one is, I mean, the name is kill, but you're going to see it. We use this procedure call to send signals to processes. And there are many types of process signals. One of them is the terminate signal, which is 9. Okay, I can send a signal 9. Signal 9 says that, okay, terminate yourself. That's one thing. But many other there are many other signals that you can send. Let's look at some of them. Okay. Okay, these are the kill signals. Let me try to find the others. Where is the others? Yeah, okay, these are the signals. Minus L, kill,
I think
minus L. You think what? Who said something?
I was about to say the documentation might be man3 kill.
Okay, kill is the name of the signal sending utility, okay? And these are the signals that you can send. Minus 9 is the kill signal, okay? Terminating it. The rest of them, some of them are defined, some of them are not defined, some of them implemented, some of them are not implemented, okay? And let's see, sig, quit, trap, term. I am trying to find the signal that suspends the process, not kills it. Can I find it with the manual page?
Sig int, interrupt.
I am not sure it is that one. List the signal in a okay, in a nice table. Okay, let's look at the nice table. We are looking at this. What? It's the same thing. Okay, I think I need to look it up from the web. Okay, I need to look it up from the web.
Also 19.6 stop.
What's that?
19.6 stop.
Maybe it is that one, but I need to look it up from the web. I don't want to go into detail. So there are many types of signals, and when you send them when you send them to a process, okay, the process has to handle it. The process has to handle it, and killing is one of them. Okay, so you will say that I am writing application program, I am compiling it with my GCC, but code to I never write code to handle a signal such as the kill signal, but it is produced automatically by the compiler. Okay, every Unix process has to handle these signals. If you don't handle them yourself, a default version is there. Okay, so it is like an operating system is sending you a signal, and that signal is automatically handled by your default signal handling function. So it's like a callback function, and it is available in your code. It is available in your code. If you don't have it, as I said before, if you don't write it yourself, the compiler will provide one, or the operating system will provide one. And the time, as the name implies, gives you the time since January 1st, 1970. Okay, good. So these are just an overview, okay? I didn't go over all the 100 procedure calls. We just looked at them. We just look at some of them. Okay, so let's look at this memory layout. Every Unix process, okay, has this structure. I have my address space. What is address space? Address space is the addressable memory locations by your process. Okay, by your process. And it starts from 0000 and it ends at some large number depending on your operating system structure, available memory, or your relationship with the operating system, etc. So it always starts with 000. Again, we are talking about Unix, and it ends with some large number. some large number. At the beginning of your memory locations, you have your code. Okay, you have your code. Your code is there, and usually this code place, okay, wherever you write your code, is readable, of course, by yourself, but it is not writable. You are not supposed to write in your code while your program is running. If you like to use some data, then you have some space, your heap space, data is here, and your stack is at the top of your memory, and it grows downwards, your heap grows upwards, and there is a gap here. That gap is the available memory for you. So if you look at the overall memory, physical memory, let's say this is your 0000 memory location, this is your operating system, this is your process number 1. Let's say I have 2 processes only, which is not realistic, but so this is the code for process number 1, data, and your stack, and this is the gap. And I didn't like what I draw here. Sorry, I am going to draw it again. Okay, I am going to draw it again. This is my memory. This is my operating system. OS, let's say process number 1, process number 2, P1 and P2. This is your, again, text, data, stack, and this is the gap for process number 1. This is again text, code, data, stack, again gap. Let me try to put a different color here. 1, no, I did it wrong, sorry. Here is 1, this is process 1, and use a different color for process number 2. Okay, this is 1, this is 2. Okay, good. So what did the book say? The book says that this starts at 000. Okay, if this is address 000, let's say, and this is address F, 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 how come the text here for the P1 is 000 again? The process 1 thinks that its address space starts at 000 and it ends with F, 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 F. And process 2 thinks the same thing too. But in physical memory, the 000 is here, and very large number here. Okay. How does this happen? How can this happen? Okay, there is this physical address here, but each process thinks that they have their own address spaces, which starts from 000 and ends up with this large number. But it is not as large as the physical memory, because I need to put, as you have seen, I need to put hundreds of processes in my memory. Can you take a guess how could this happen? It looks like there are 200. Oh, there are many. Okay, there is this 000, there is this 0, and there is this 0, and there are as many zeros as process numbers, right?
Maybe it divides the memory into pages.
Say that, Usama, again.
Maybe it is dividing memory into pages, so like sections that you get.
Yeah, something like this is happening, but each process thinks that they have their addresses are from 000 to FFFFF.
Maybe operating system creates virtual memories for processes, and each process thinks it's using the whole memory.
Yeah, yeah. Operating system is setting this up, but remember what we said. What did we say? When our programs run, okay, they freely write anything to their memory locations without asking anything to the operating system, right? They have the CPU, they have the memory, and they run, okay? So each instruction is not monitored by the operating system when they are doing the right thing. Okay. So I mean, memory reference is not an operating system call. You just access your memory. That's it. You will say that I like to read the memory location 0007. That's it. You could do that, right? In a C program. In a C program, it is possible to say integer pointer P is 0x007B. You could say that, right? And this address is yours. And I can do this in two different programs at the same time. Still, they are using their own memories. They are not referring to the same location. They are using their own memories with the same addressing. How this happened? This is called memory management, and that's the topic of the chapter number 3. Okay. First, we are going to look at the processes. Then we are looking at the memory. So memory is virtualized. Memory is abstracted by the operating system and the hardware. Without getting help from the hardware, we cannot do this. Remember the system structure, a simple computer structure that I showed you before. We said that this is simple, but okay. Remember this MMU, memory management unit. Memory management unit is responsible for providing this virtualization. Okay, for each process. Okay, for each process, when the process P1 says that access this memory location, it is the task of the memory management unit to virtually, okay, provide this abstraction. Okay, when process 1 says that I like to access the address number 007, MMU knows that P1 should use this location, P2 should use this location, etc. Okay, so we are going to look at it. We are going to look at it when chapter number 3 comes. Okay, so operating system, it needs the help of the hardware, MMU. Who controls MMU? Operating system controls MMU at the beginning of the system boot up. Okay, so operating system does two basic things actually. Abstract the CPU. Each process thinks that they have the CPU for themselves. Also, each process thinks that they have their own address space, and they are free to use whatever they want with that address space. Okay, so let's go back to our slide again. Okay, so this is the memory layout, and each process thinks that they have such a nice structure, and each process thinks that this is my address, and each process also thinks that I have a nice CPU, and I can run my data on the CPU, and everything is fine with me. They don't know, they don't realize that they are sharing the same memory, okay, larger memory, physical memory, or they are not they don't know that they are sharing the same CPU with many other processes. Okay, so let's look at this linking stuff. Let's say I have two directories, user AST and user gem. Okay, and in Unix we call this inode or index node structure file system. Okay, each file, whether it's a regular file or a directory, doesn't matter, has a index node. This directory named mail, games, and test, they all each have their own inodes. Okay, and these inodes are unique across the system, the whole file system. Okay, and the user gem has 1, 2, 3, 4 entries in it. Some of them are directories, some of them are regular programs. Okay, regular files. Okay, when I execute this linking command or system call, procedure call, I am saying that I am going to link user gem memo. Okay, user gem memo, this one. Memo is a directory, I guess, or maybe a text file, I don't know. With this file, user AST node, there is no node, so a file name node is going to be made here, but as you see, the index number 70 and memo 70 is the same. So this node and the memo are the same thing now. Okay, although their name looks different, if I open this file, I am opening this file actually. Okay, if I modify this file, I am modifying this file. So this is called linking, hard linking. There is another way of doing this, is soft linking. We are going to see it later. This is called hard linking, and it is done with the inode system like that. Okay, so we are going to talk about it, and you are going to talk about this in your systems programming course too. What else? Mounting is another frequently used Unix command. Okay, this is my directory structure. At the root, I have my bin, devices, libraries, mount location, and the users. When I execute this command, mount my device SDB0. What is SDB? I mean, usually you would understand what kind of device it is. SDBs are special disks. I don't remember what they are. Dev SDB. Usually you would have a disk number or something like that. Or I don't know what kind of device it is. So this is the device driver actually. You are mounting this device to this directory location. Okay, after so this is a disk. I mounted the disk under this mount location, so the structure of that disk is now mounted here. So in Windows, usually this is what we have in Windows. When I open up this command script, okay, command shell, I have my C drive. Okay, do I have a D drive in here? No. I don't have LS, right? Sorry, I have only a single disk on this computer. If I had more than one disk, then it would have been D or E or F. No, I don't have any of them. So this is how you switch between two drives in DOS-based computers or Windows-based computers. But in Unix, you have a single root. Using change directory commands, you can switch from the single root to the other roots. Doesn't matter how many disks you have on your system. It is nicely mounted in here. Okay, so in my Unix thing, if I say what did I mount so far, okay, my C is mounted. There are many things mounted. Device PTS. Okay, the keyboard devices and etc. mouse devices, they are all mounted. Oh, I know how to make a new drive. No, I cannot, because if I do that, my camera will go away. Sorry, I was going to insert a USB disk, and that was going to make a D drive or something like that, but I don't want to take my keyboard, the camera out. One of the cameras, I'm connected with two cameras. Okay, so many of these, that I want to show you some differences between Unix and Windows. Okay, what else? I have ch mode. Change the mode of a file. When I say as minus L means long version, so each file has their own access permissions. This one says that for the user it is read write, for the group read write, for the others read write again. Okay, if I like to change mode, group minus read write x, and what is, I don't know what linked txt, but if I do that, so I took all the read write execution permissions from the group for that file. And if you get the file now, I don't have it. So this is a simple way of granting read-write execution permissions. Time again returns the time since 1970. If you have a 32-bit computer, then you have at most 2 to the 32 seconds since 1970. That's more than 136 years should be enough. With the 64-bit computers, this is more than enough. Okay, that's how you make system calls with the Unix. How about Windows? Okay, Windows has a API too, but it is not POSIX compatible. Windows doesn't implement any POSIX compatible API. It has its own API, Windows.h. If you like to make system calls with the Unix, you include Windows.h in your code, and you have many system calls. And what did we say? POSIX defines 100 procedure calls, and Windows defines thousands of procedure calls. Again, we don't call them system calls, but we call them procedure calls. Okay. So the Windows operating system doesn't actually tell you what are the actual system calls. It says that, okay, you have Windows.h. You make your procedure calls and I will handle them. Some of them will be really system calls and some of them won't be system calls. It is up to me which one it is. Okay. And I get to change it. I get to change that decision from one version of Windows to another version. But I promise you, I will keep this Windows.h for you. I may change the Windows.h. I may change the Windows.h, but your functions will be there, so you can change, you can call them. Okay, so this is a nice table that kind of compares Windows.h with the POSIX procedure calls. As I said before, Windows offers many more procedure calls in the order of thousands. Okay, because graphical user interfaces are parts of the Windows operating system. Unix doesn't say anything about the graphical user interfaces. All the Unix says is those kind of procedure calls. Okay, let's do some comparison. For Unix, to make a new process, you would use fork. For Windows, it is create process. Okay, the create process is something like this. Create process is fork plus execve. Okay, so we don't have exactly the same thing in Windows. Okay, for wait PID, you have wait for single object. There is no execve in Windows. Is that what did I say? Create process is fork plus execve. Okay, exit process. Okay, open create file, close handle. Okay, this create file creates a file or opens the existing file. It is done at the same time. Okay, reading for writing, seeking, get the status of the file, creating directories, removing directories. There is no linking, unlinking, mounting and unmounting in Windows. Okay, what else? Changing the directory. In Windows, we don't have chmod. Okay, because in Windows, we don't have the permissions for the file originally. Okay, there is no signal mechanism in Windows, but you could get the time, of course. Okay, so if you have a program written for Unix environment, C program, of course you could compile that program for Windows environment, but if you have this kind of stuff, linking, unlinking, and signaling for that environment, you won't have them in original Windows. Okay, so you need to use some kind of a library to handle those kind of system calls for Windows, which are available usually, but you don't have the exact system support for these kind of calls, such as the sending a signal to a Windows process. Okay. Any questions about the differences between the Unix and Windows? It is very helpful to it is very helpful to refer to the real operating systems to understand what is going on, and it is also very helpful to make comparisons between the existing operating systems. Also, it is very helpful to make comparisons between the modern operating systems and the historical operating systems, even if they are not being used at all. Okay, any questions?
Sir, why didn't Microsoft decided to use Unix when it created these, let's say, functions?
Why why Microsoft did not use the POSIX interface? Okay, well, I mean, it is all historical. I mean, Windows was based on DOS, the disk operating system, and the DOS is a very simple operating system. Some people wouldn't call it an operating system, but it's an operating system actually. During the first days of DOS, you had you have this processor, okay, 8086 processor, Intel processor. This processor was very weak, okay. It couldn't give any protection. There is no memory virtualization, and it was very difficult to have multi-programming with this one because it didn't have protection. So if you don't have protection, if you don't have virtualization, your whole operating system changes because there is no mechanism like fork, because if you make a fork, your child process is not going to run at the same time. So the original DOS was a multi-programming operating system. It didn't have any virtual memories. And the disk system it uses was very simple. I know it was too heavy to implement on these kind of systems. Since like that, they couldn't have any powerful operating system on that kind of a computer, so they kept it simple. But later, when the computers get more and more powerful, those started having similar stuff to Unix, but historically they had to support the previous versions. So what they did was they continued supporting the older versions of those, and historically we have something like that. Okay. We don't like it much. Okay, Windows people don't like it much, but it is historically it's the same thing. So it's something like that. Okay, you take a plane and you look at the structure of the cities like Istanbul. Okay, you would ask, why do we have roads like this? The road should be like straight, right? It should be wide and straight, so, and it should be easy to find stuff. But in Istanbul, it is not like that. Okay, you cannot find a road that goes straight. It is always taking a curve. Sometimes it gets narrow, sometimes it gets low and high. Why is it like that? It is because of the historical reasons, right? Usually the roads follow the creeks and the rivers, and they try to go around the hills and etc. After 100 years, all the creeks and the rivers are dry. You don't have the hills anymore, but your roads stay that way. Okay, roads stay that way. It's something like that. We don't like the existing structure. So what are you gonna do? Maybe one thing that you can do. The Apple operating system started like that, but in the 2000s they made a decision that okay, whatever we are doing, we are going to ignore it right now. We are gonna make everything based on the BSD Unix, right? The Apple operating system is based on the BSD Unix. Okay, they made that decision. So they started from over. Windows didn't do that. Or like the Napoleon decided that, I think he lived in 1800s. He decided that this tip Paris is too unstructured. I have the money. I got all the money from the wars. I killed lots of people. I took their money. So what am I going to do? I am going to demolish the whole city Paris. Okay. I am rebuilding the city. That's why they have the most straight and the longest avenue of the whole world, the Champs-Élysées. I think that's the road. That's how they did it. Their cities are so structured. Okay, at least that part of the city. They couldn't do it in Istanbul because they have too many historical structures. They didn't have that much money. Well, maybe they are doing it with this kentsel dönüşüm projects. They are doing it with the what? They are doing it with the Gecekondu parts of the city. Well, they try to do it, but I don't know how successful they are. Okay, I mean many things in computer science, like the operating systems, programming languages. If there is a decision made, it is usually historical. If you don't understand it. Okay, any other questions? Okay, if there are no questions, let me stop here. Let's take 10 minutes of break. After the break, we will be here 11:32. 10 minutes. Okay, so um, so this is the two operating systems that we looked at so far. I mean, we didn't look at them in the detail, but the important thing is it's their interfaces, Windows.h, Windows API, and the POSIX structure. Let's look at a little bit about the structure of the real operating system. Okay, how do you design an operating system? What kind of structure do you follow? Okay, that's what we're gonna do. Okay, the most common, the most straightforward, and historically the most preferred way of doing the operating system is designing the operating system is the worst one, the monolithic approach. Okay, the entire operating system runs like a single program, like a single process, and it is trying to handle everything. Okay, so this is flexible because you can do whatever you want as an operating system, but it is difficult to debug, it is difficult to add new functionality, it is difficult to find the errors and make modifications, etc. Okay, if there is a single crash in your operating system, then the whole operating system is going to go down if you don't follow any structure. So this is the monolithic structure. If you keep your operating system as a single process, so people said that we need to get some kind of a structure with our operating systems. So what are we gonna do? Maybe monolithic operating system structure, again, single process for the whole operating system. Maybe we can do this. Okay, simple structuring model for monolithic operating systems. Everything is a single process, but entry point is here, main procedure. Then we have our service procedures. For example, I need more memory, I need this file to open, I need to do input output, I need to do network connection, etc. So these are the service procedures, and they are isolated from each other. Of course, they are sharing some basic utilities. Okay, so the basic utilities are there, and each service procedure can call some of these basic utilities, and that way, if you have a problem with the file system, you know that it comes from this service procedure. I need to fix it here. Or if you like to replace your file services with something else, then you know that you are going to replace this service procedure module. Okay, you know this one, but still everything runs like a single process. If there is a crash with your operating system, the whole process is gone and you will be in trouble. So this is the monolithic operating system. Okay, so the main program invokes the requested service procedures. Service procedures carry out their tasks. While they are doing it, they get the help from the utility procedures. And not all the utility procedures are in the memory actually. Some of them are DLLs. Okay, they are loaded to your memory whenever they are needed. Okay, so this kind of layer structure was common from the first days of the operating system. From 1960s, THE operating system from Netherlands. Okay, I think that the author of the book was involved in the design of this operating system. Okay, it is structured this way. At the top layer you have the operator, then user programs, then input-output management again, operator process communication, and memory DRAM management. DRAM is the disk, okay, and processor allocation and multiprogramming. So the multiprogramming is at the lowest level. These are the most basic operating system services, and on top of it you have this. So the whole operating system is designed that way, and the rules are followed. And if you are going to change something about the input output, you don't deal with these layers. You come to the layer number 3 and you change your structure, or you add new input output management stuff, and etc. Okay, and while you are doing this, you are only using the services provided by the operator process communication. So this is the structure of that operating system. Remember Multics. Multics is the most important operating system if you are a Unix person. Okay, and most of the world, as you know, the Linux is the most popular operating system because Android is based on that, right? So the Multics is the ancestor of all of these operating systems. In Multics, instead of layers, they had rings, okay? At the center of the ring, you have your process management, okay? And then you have memory, and then you have input, output, etc. And then you had others. Okay, you would say that what is the difference between this structure and the layered structure? This structure is supported during the runtime too. So the hardware knows that you are in ring number 0 or 1 or 2 or 3 or 4, okay? If you are in ring number 4, your CPU, hardware knows it, and if you like to do something else that belongs to ring number 2 or 3, the hardware will stop you from doing that. It is going to cause a trap. It's going to cause a trap. So Multics is designed this way, and this design is supported during the runtime too. Okay, during the runtime too. Well, you may say that, I mean, it is the same thing. I mean, I designed it this way. Whatever I do, it has to be followed in the runtime too. But I mean, by accident, if the main procedure calls something in the utility procedures, it will not be detected during the runtime. Okay, that's not detectable. But with Multics, it is with the help of the hardware, it is not possible. Okay, so Multics is designed that way. Okay, so we are going to talk about Multics a lot because it is ancestor of the Unix operating system. Okay, then another idea for structuring the operating systems are microkernels. Okay, microkernels say this. Okay, if you are a regular human being, every 1,000 lines of code, you are going to introduce one bug to your code. Okay, humans make mistake. Beşer şaşar. Even if you are a PhD, very well educated, very smart programmer, doesn't matter. You are going to introduce bugs. So if you have a monolithic operating system, okay, of 5 million lines of code, you would expect that you are going to have between 10,000 and 50,000 kernel bugs. Okay, in your kernel, you are going to have this many bugs, and each one is very potential security problem. Each one is a very potential critical problem because it is the kernel, right? Okay, so that's a very large number. So what are you gonna do? You might say that let's not use humans to make computer programs. That's not possible for now. So the idea is let's keep our kernel small. Okay, that's why we have microkernels. So this Minix 3 operating system, which is developed by the author of the book Tannenbaum, okay, says that the Minix 3 microkernel is only 12,000 lines of C code and 1,400 lines of assembler code. That's it. So you would expect that there are around 10 to 20 bugs in the Minix 3 kernel. So how do you keep your kernel small? So well, you only keep only the necessary stuff in the kernel. For example, interrupts. I have to handle the interrupts in the kernel. Okay. Process management and scheduling and inter-process communication. Okay. So that's what I keep in the kernel. All the other stuff, including the input-output stuff, networking, printing, terminal stuff, file system, okay, all the procedure handles, the reincarnation, shell, and etc. They are all in the user mode. You might say that, how can I have our drivers in the user mode? I mean, drivers are very low level programs, right? They need to access the special registers on the device driver, special registers on the controllers. How could this happen? Of course, that the driver is going to ask this through the kernel. Ask the kernel to read some data from a controller. Okay, so all the time you need to make lots of system calls. So what is the problem with making lots of system calls?
Makes it slow.
It makes it slow, right? Because it is context switching. Making lots of system calls is expensive. You need to switch from the user mode to kernel mode. When you do that, the CPU has to save lots of stuff. When you go into the kernel mode, it is not guaranteed that it is going to come back immediately. So the downside is inefficient. Of course, they dealt with this problem. They say that we can make this efficient and etc. But it's still a problem. There is an interesting server here, the reincarnation. It says that my job here is to check if the file system is alive, if the all the drivers are alive, everything is alive. If they are not alive, I will reincarnate them. I will relaunch them. I will start them again. So this one is trying to see if any part of the operating system is dead. Okay, if it is dead, it's like a watchdog. Okay, if it is dead, then it starts it again. So this operating system is very resilient. It is very robust against these kind of problems. Okay, so a microkernel idea is like that. Okay, keep the kernel very small. So you are handling many things in the user mode. They say that let's keep policy and the mechanism different. Okay, policy is the procedure itself. What is the policy of the disk access? Okay, how do I do that? Okay, what are the algorithms? All the algorithms are called policy. Mechanism is the reaching the disk itself. So mechanism is not that smart, but it has to be privileged. So the policy is it is the complicated part. Keep the policy algorithms and everything, all the code in the user mode, but mechanism, which is the stupid stuff, but it has to be saved, it will be in the kernel mode. Okay, good. So the idea of having the drivers in the user mode is very smart. The most of the time, 90% of the time, your Windows operating system is crashing is because the drivers from the third-party providers. In Windows, you have to run your drivers in the kernel mode, right? But who writes the drivers? Microsoft doesn't write them, right? The drivers come with the devices, and whoever designed the device, I don't know who they are. You need to trust them, but not all the time you can find very trustable drivers all the time. So you need to run some code from a third-party provider, and they will cause those blue screens. Okay, so when the Windows crashes, actually it crashes because of these drivers most of the time. It's not going to happen with microkernels, because if one of the drivers crash, that driver is going to crash only. Okay, it's not going to take the whole operating system with itself. Okay, good. By the way, Microsoft is doing this similar kind of stuff with this reincarnation stuff. You know, overclocking. Did anybody do overclocking?
Never did it, but it is just increasing the power consumption of the CPU or something like that, so it will run faster.
It is not power consumption. It is you are increasing the clock rate of the CPU. If your CPU is designed for 1 gigahertz, you are trying to run it with 1.2 gigahertz. So it is faster, 20% faster, a lot faster. So why don't we do it all the time? Because if you run your CPU a little bit faster, it is going to overheat and it will start giving errors, like it is going to execute some of the instructions in a wrong way, or it's going to miss some of the memory references, etc. Right? That's not a good thing. Okay, so most of the time when you overclock your computer, your system crashes. But with the recent Windows operating systems, Even if you overclock your system, operating system doesn't go down. It just keeps running. Your program starts giving error messages. Okay, your Word, your Excel, your web browser, they will crash. They won't do whatever they want. But operating system somehow finds a way to keep itself running because it has these kind of servers somewhere. If something crashes, it just relaunches it. It is very resilient actually. Okay, so these kind of ideas are already exist in the other operating systems too. Okay, let's continue. Client server model actually gets the idea from this microkernels. Of course, historically it is not. It doesn't get the idea from micro, but it is an extension of the idea. Let's keep the kernel very very small. All the kernel does is, okay, whenever a request comes, it it communicates that request to the file server or the process server or the terminal server. Kernel is just a communication mechanism. Okay. Also, the kernel runs in the privilege mode. Privilege mode. So if this is the structure, if my file server, process server, terminal server are all different, and kernel is the only way to reach them, okay, why don't I keep all these machines on a network? So this is a distributed operating system. My file server is very simple. Very small part of my server is in the kernel. Very small part of my process server is in the kernel, etc. Okay, so everything can be run on a network, and all the communication between these servers are done using message passing. Okay, so this is called the client server model. If the terminal server crashes, then somebody else can relaunch it. It's not going to affect this process server or the file server. Okay, so that's the idea of the client server model, and it's good for distributed operating systems. Of course, all these machines could run on the same physical computer, but the structure is like that. Good. So maybe from this on, we can look at this virtual machines too. The idea of virtual machine is like that. Again, the idea is from 1960s, from the IBM mainframes. Okay, this is my hardware, this layer, my CPU, memory, input output devices, etc. Usually on top of hardware we run our operating system, right? They said that no, let's write a layer of software which is called the VM, virtual machine. Okay, the task of that virtual machine, okay, provides several virtual machines next to the next layer. So this layer makes it possible for the upper layer so that they can think that they are using the real hardware. Okay, so this CMS is an operating system and operating system. This CMS operating system, whenever it needs the input output instruction, okay, it thinks that it is accessing the input output device, but it is causing a trap, and that trap is handled by this VM 370. Okay, and this layer is responsible for virtualizing this hardware so that the upper layers, they think that they are using some kind of hardware, but all they are using is virtual hardware. Okay, so this is the application that runs on the CMS. What does the application do when they say open a file? Open a file means that system call comes to the CMS. Okay, the CMS has to do some input output, but it doesn't have the real hardware. So when it tries to access the IO device's memory location, it traps to this VM software. Okay, it is not doing a real input output. So this VM software knows that there are 3 operating systems running on top of it, so it does the real input output for this operating system, and it is handled that way. Okay, so each virtual machine is identical to the true hardware, and the CMS could have run, actually this CMS could have run on top of this bare hardware actually, but it doesn't. It runs on some kind of a virtual layer, but it doesn't know about it. So on the same machine, very expensive large machine, I am running 3 different operating systems or 3 copies of the same operating system. One is for the maybe, if you think about the university environment, this is for the students, this is for the researchers, and this is for the administration staff. Okay, and this is secure. Okay, if the one of the researchers is doing something very expensive, very time sensitive, it's not going to affect that much these two, because these are real operating systems. Of this, or for some reason this one crashes, somebody hacked it, these two are still alive. Okay, so the idea is from 1960s, and these were valid, and people were using this from 1960s, 70s, 80s. Okay, but in the PC world, when we have the Intel processor, the Motorola processors, doesn't matter. We didn't have this kind of a structure. Why? Because we didn't have this functionality with the early Intel processors. Okay, if you are a regular program, see, the CMS is a regular program here. Okay, it is not running in the kernel mode. This one is running in the user mode. When this one runs in the user mode, but it thinks that it's an operating system, if this one tries to access, if this one tries to execute a privileged instruction, then regularly it's going to cause a problem. But with this hardware, it says that no, when this regular program tries to run a privileged instruction, it's going to trap to this layer. With the Intel processors, we didn't have this functionality. Later, they added this in 2000s. Okay, later they added this 2000s, and in Windows environment or the Unix environment, we started having virtual machines now, like the virtual machine that you are using for your homework, right? That virtual machine behaves like a regular operating system, but actually it's running on a virtual environment. It is all possible because our new processors and our new operating systems support this kind of mechanism for our regular PC based processors. Okay, that's what it says. IBM has had this virtual machine available for the last 30 years. We started having this functionality in 2000s. Okay, and companies like virtualization a lot because they have a large server computer, even a mainframe, and they run different operating systems on it. One for the mail, one for the web, one for the CPU server, and etc. If the web server crashes, our mails are still working fine. Okay, so the idea is this: when an operating system running on a virtual machine, and if an operating system executes privileged instruction, okay, so usually if you are in the user mode and if you are trying to execute a privileged instruction, your program will die, etc. In this kind of processors, the hardware says that, okay, I'm causing a trap because somebody is trying to execute a privileged instruction. So what does the virtual layer do? The virtual layer says that, okay, I'm going to get that instruction, I am going to emulate that instruction in software. It's going to be a little bit slow. Maybe I will get the help of the hardware, but that system will think that it is doing real I/O. That's what happens with the virtual machines. Here is one good example of virtual machine pictures on regular systems. 2 types of virtual machines. We are going to look at them later at the end of the semester. The type of virtual machine that you are using for your homework is this one, type 2 hypervisor. What is hypervisor? We have the supervisor. Usually for our regular operating systems, the scheduling between the processes are handled by the supervisor. Okay, so the regular operating system, the scheduling is done with the supervisor. But if you have a virtualization layer like that one or that one, these are called hypervisor. Okay, hypervisor is one level over the supervisor, and this type of hypervisor runs on the host operating system, for example Windows. On top of Windows, you have the hypervisor, and there is a guest operating system. In your case, with your homeworks, the machine that we are going to provide you, okay, is a Ubuntu guest operating system. And on top of it, you are running your editor, you are running your compiler, you are running your shell, etc. And I am actually doing the same thing with here too. Okay, this one is running some kind of a hypervisor provided by the Windows, and this one thinks that it is running on a regular Unix operating system, but actually it is not. Okay, and this is type 1 hypervisor. This type 1 hypervisor runs, okay, there is, of course, this is hardware and this is hardware, right? Okay, so we are going to look at them later at the end of the semester. Virtualization is very important. It makes you use your hardware in a much efficient way, and without noticing by the without any noticing by the users, by the operating system. You may add many more operating systems to your system if you are underutilizing your hardware. Okay, something related to these virtualization is the Java virtual machine. You know about this, right? With the Java virtual machine, you have with the Java virtual machine, you have your hardware. On top of hardware, you have operating system. On top of hardware, you have Java virtual machine. On top of Java virtual machine, you have your bytecode. Your application, Java application, runs here, right? So your Java application doesn't talk to the operating system directly. When Java application says that open, okay, it is not a direct system call, okay? That system call is translated by the Java virtual machine. Java virtual machine knows on what kind of operating system it is running on. If it's a Unix operating system, okay, then it makes an open system call. If it's a Windows operating system, it makes a create file system call. Okay, so that's why Java virtual machines are different for each type of operating system. Okay, good. So what is the advantage? Advantage is your compiled code can run anywhere you like as long as there is a Java virtual machine for it. Good, any questions so far? So what are the virtual machines are nice, but what are the downsides of virtual machines? This is nice. This is nice. In computer science, in any engineering world, if you have a nice idea, you may introduce lots of advantages with it, but usually there would be downsides too. There would be disadvantages too. So what would be the disadvantage of virtualization, virtual machines?
Slowing down our applications.
Yeah, it is like the operating systems. It would slow our applications, or the hardware, the bare hardware has to run now 1, 2, 3 operating systems, and on top of that a virtualization layer. This is software again, right? This is software, right?
Other than that, I think it may introduce some bugs depending on how well the virtual machine is implemented and
Yeah,
how well it communicates with the original machine as
yeah.
well.
Usually they are not as robust as running your hardware, running your operating system on the direct hardware. Okay, you're going to introduce some bugs because this is software. Software means that every 1,000 lines of code there is a bug, right? So I am going to introduce those, and those are the bad sides of it. Okay, good. So let's continue with the virtual machine. We talk about the Java virtual machines. So these are the operating systems again, virtual operating systems. And then a new type of operating system structure, exokernels. Okay. Exokernels are like virtualization layers, but they are much lighter. Okay. So what they do is okay, let's run the virtualization, but in a way that you don't make the hardware fully virtual. You say that this part of hardware is yours, this part of hardware is yours, and this is yours, and that's it. For example, if I'm going to share the desk, okay, this is my desk, okay, it would say that this green part would be the operating system 1, and this red part would be operating system 2, and this black part would be operating system 3. So what is the advantage of it? All the operating system 1 is going to do is to access the cylinder number from 0 to cylinder number 100, okay, or 1024, okay. So the virtualization layer doesn't do much, okay. After doing that, that's why it is called exokernel. After doing that, okay, all the mapping will be very, very easy, okay, and this is going to be much more efficient. So the virtual machine monitor must maintain tables to remap discard addresses, okay, in the other designs, but in this case I don't have to do any remapping, okay. All the addressing is done by the original operating system. Previously, the virtualization layer has to say that, okay, this operating system is trying to access from this location, but I have to remap it. I'm going to change that address, but it will think that it is accessing the original location. Exokernel doesn't say that, okay. Whatever the operating system is trying to access, as long as it is within these limits, then it should be fine. It's called exokernel. Okay, good. So that's one operating system type. So any questions about the structures of the operating system? Well, these are all ideas used by the current operating system designers. If you ask a question, how about Windows? What is Windows? Is Windows like an exokernel or a virtual machine type of thing, or the client server model, or the microkernel, etc., right? Or Unix, or Ubuntu, or that kind of stuff? The answer is no. The operating systems use all kinds of ideas from each type of operating system structure. Okay, so the microkernel idea is used. Of course, virtualization idea is used. Exokernel idea is used by the modern operating systems. So you wouldn't say that unless it's for example, this Minix is an experimental operating system. You cannot buy it. Okay, it is free, but there are the drivers are not available for all the devices for the Minix operating system, and there is no company that kind of gives you support for the problems, okay, unlike Windows or Ubuntu. With the Ubuntu, if you are paying for the Ubuntu server, if you pay money, okay, there is a company that will give you support to fix problems, to give you more flexibility with your commercial operations. With these kind of operating systems like this Minix operating system, since it is only for research purposes, you cannot get that kind of a commercial support. That's why they can say that I am such an operating system. I'm a microkernel. I am not going to do anything else. Okay, because I am trying to make a point here. Microkernel is the idea. Okay, for the older operating system, as long as it works, they are going to use ideas from different operating system structure types. Okay, good. Any questions? Any questions? Remember, operating systems are pieces of code, large code, but pieces of code, and code has to be designed. You just cannot start writing your code, right? It's a software. Software has to be designed. You need to figure out the requirements, okay? You need to make a main design of the system. You need to implement it, and you need to have ways of testing it. And you know that software is never finished. You are going to keep adding to it, make modification, make it more efficient, do lots of iterations. So operating systems are no exceptions, and you are going to do this kind of, you are going to go through this kind of phases with operating systems too. Okay, I am going to continue with, at the end of this chapter, the book says that let's look at the C programming language. Okay, why do we have the C programming language? We have the C programming language because of the Unix operating system. They developed C programming language to write the Unix operating system. That's why they said that, okay, C has to be a high-level language because it is difficult to write programs in assembly or machine code. But at the same time, it should be flexible enough to write the operating systems with, okay? So C is developed that way and people liked it. It is so efficient when you compile your C code, okay? It is maybe 80% as efficient as the assembly code, okay? It is very close. It is not as close as efficient as assembly, but it is still efficient. So C is good. With the C, of course, you know, our pointers, memory allocation, free, and all kinds of POSIX system calls, okay? POSIX procedure calls, they correspond to one C library function. We have C header files, you know that, right? The header files are our interfaces. With the header files, with the help of the preprocessor directives, like if I am running on a Intel platform, okay, then I am going to define an acknowledgement function. Otherwise, for the Motorola platform, I don't have that kind of thing, okay? Large programming projects, millions of lines of code is possible with the C language because you get to divide your program into many different C files, okay? And for each one, I define my interface with the other file, okay? And this is what we do with the C, right? You have your header files and C files. You pass them through your C processor, okay, C preprocessor. It will get rid of all the defines and it will make all the includes. Then I will compile them. It will produce my object files and I will link them with the libraries, and this is my executable program. This could be your operating system kernel. This could be your application. This could be your system program. And starting from 1970s, we have been following this procedures. Okay, we have been following these procedures for writing application programs or the operating systems. Okay, all the modern operating systems are written in C, including Windows, including Linux variants, or the Android, or any operating system that you can think of. Of course, there should be some part with the assembly, but mainly things are written in C. Okay, good. Any questions? Any questions? At the end of this chapter, the book, this is the cover of the book. So we covered all the operating system stuff, kind of. Okay, we know what memory is, we know what CPU is, processes are, input outputs, operating system structure, and the author of this book likens it says that the operating systems are like circus. Okay, the circus are, there are many exciting stuff. There are some stupid stuff too, and many things are happening, and we are kind of watching it. So that's why they have this comic picture, and we are going to see some of them. Client server structure. Okay, if you don't do your process scheduling, things are going to go bad. Okay, this multiprocessor guy is doing many things at the same time. We will see there will be lots of race conditions. If two processes are trying to reach the same resource, that's going to be bad. What is FAT? FAT, file access table. Well, I mean, FAT doesn't have anything to do with the biological fat or these kind of animals. Layered software, middleware. Somebody is interrupting something anyway. Okay. Okay, so we are going to look at these one by one. So after the end of the picture, end of the semester, you will go back and look at this picture. I don't like this picture, but this is the picture from the book. Okay, any questions? If there are no questions, then I am going to start the next chapter, which is about processes. Okay, chapter number 2.
Now, here's a small question. Why do why do operating systems use C rather than C++? Since
No,
C++,
but
it's
when I say
designed.
C, I meant C/C++.
Oh, okay.
They still like to use the ideas from the object-oriented world, right? Write lots of classes, and they are written actually in C++. Even if you write them in C, you use ideas. You use ideas from object-oriented programming languages, like write structs, and some of the struct elements are accessible to the outside world. Some of them are not. Of course, the compiler doesn't directly support this idea, but if you write your code in a way that you don't access some of the elements of the structs, okay, from outside, then you are following the object-oriented philosophy, right?
I see.
Okay, so processes and threads, chapter number 2. What did we say about the operating systems? They abstract away the details of hardware from the programmer. And our most important piece of hardware is the CPU. Let's 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 try to abstract away the details of processor, the CPU, from the user. So the idea of process is born, okay? So process is an abstraction of a running program. A running program is called process and is an abstraction actually, okay? We abstract away the sharing of the processor between many processes. If you are writing a program, you don't care who else is using the CPU or the memory. So whose task is it to make this abstraction or make this possible? Of course, the task of operating system with the help of the hardware. Okay, so the processes are one of the oldest and most important abstractions that the operating systems provide. They are oldest, okay, with the idea of multiprogramming. Remember, multiprogramming was very useful to make use of every CPU cycle. Whenever your program is waiting for input output, okay, I switch from one program to another program so that I can keep using my CPU. That was the idea. That is oldest. It is important. Why? Because without the abstraction of the processes, the CPU, I cannot do the abstraction of other stuff. That's why at the lowest level of the operating systems, we have the process scheduling. Who's going to use the CPU now? Remember our microkernels? Remember our microkernels? Okay, let's go to the microkernels. We like to keep our microkernel as simple as possible, but I cannot take the interrupts out of this kernel. I cannot. Interrupt has to be the part of the operating system. Also the processes and scheduling, inter-process communication. So in a way that this chapter number 2 is studying this microkernel part. Okay. Without these, there is no operating system. I cannot take these out of the kernel of the operating system. We are going to look at the input output, okay, file systems, etc. And if you try hard, you can put them outside of the kernel, but process scheduling, okay, inter-process communication, interrupt handling, these all have to be handled in the kernel. That's why they are important. Okay, so the idea with the process is, okay, I am going to make the process believe that they have their own CPUs. Okay, I turn a single CPU into multiple virtual CPUs. Seems like a virtualization. Okay, without the process abstraction, modern computing could not exist. Okay, this is a very simple example. On my CPU, I am running 3 processes and operating system 2. Okay, it looks like 4 things are running at the same time, but it is not actually. It is time multiplexed or intermixed. Given at a time, only one of them can use the CPU. At this time step 0, 1, 2, 3, 4, 5. Okay, so at time 0, process number 1 is using the CPU for maybe 50 milliseconds. Time 1, nobody's using it. Okay, CPU maybe sits idle. At time 2, process 2 is using it. 3, process 1 again. Process 3 is using the CPU at time 4. Okay, so who's making the decision? Who's making the decision on this? Who is going to use the CPU? Operating system does this decision. And of course, when I switch here, when I switch from process 2 to process 1, here, between these two, operating system comes in and runs, okay? Without the uh, operating system's control, there is no switching between these two processes. Operating system has to come in and has to do the switching. So let's look at this picture again. This is 50 milliseconds, 100 milliseconds, 150 and 200. These are the milliseconds. So what happens at the end of this slot number 2? So what is triggering the switch from process 2 to process 1? It is either a timer interrupt has occurred, or process 2 has asked the operating system to do something, right? 2 things happened. If timer interrupt has happened, who is going to handle the interrupt? Operating system. So operating system comes in, say that, okay, I am handling this timer interrupt. I handle the timer interrupt. Now I am going to go back to the processes. Which process should continue? Okay, process number 2 used the CPU too much. Now I'm going to switch to either process number 1 or process number 3. So it makes a decision. It says that process number 1. So this is what happens when the interrupt happens. If interrupt did not happen, but process 2 asks the operating system to get some data from the keyboard, okay, then in that case, operating system says that, okay, I'm going to get that data from the keyboard, but that's going to take a while. The user didn't press any buttons yet. So process number 2 is going to wait. I will switch to process number 1. So all the switching is done by the operating system according to its scheduling policy. Okay, but each process thinks that they are using their own CPU. Okay,
Here's a small question.
Sure.
Do operating system have priority? So this process is more important. That's why I will run it more frequently.
Sure, yes. I mean, depending on the operating system type, priorities can be associated with the processes, and as a regular user, you may change that priority. You may not increase your priority, but you may decrease your priority. In Linux or Unix, it is nice. When you say nice ls, okay, you are saying that I am going to run ls, but I am going to run it in a lower priority mode. So I am being nice to other processes, right? You may lower your priority, but it's up to the operating system to change the priority of a process. Can I find it in here? The priority of my, do I have it?
I think it is in başlangıç menü.
In where is başlangıç? Dosya, seçenekler. Where is başlangıç?
Next to kullanıcılar.
Okay, next to kullanıcılar başlangıç. Oh, these are the processes that I like to start when the system starts, right? Yeah.
Yes.
I hate this one. I am going to take this out. Oh no, it is not effective. Yeah, okay. Where is my priority? No, I don't see it. Maybe it is in the details. Yeah, PID, CPU. Can I add, like, I think there was an option that lists all the data about the processes, but I forgot where it was.
Process, right click.
Right click and then, yeah, see, this is the priority. Let me make this higher, very high priority. So it might cause some instability. Okay, I'm doing it. Since it is my priority, it's my process, I could do that. I think I increased it. Okay, so you can do that. But I mean, these kind of things have very unexpected results. I mean, increasing the priority of a process sometimes causes just the opposite effect, and we are going to see it in the chapter. Okay, any other questions?
Okay.
I think I am out of time. We will continue tomorrow morning then. I'll see you tomorrow morning. Okay, take care.
Have a good day, sir.
You too.
Have a nice day.
You too.